Hey everybody. So this is a unique and interesting research paper called FNet, mixing tokens with Fourier transforms. And this is an older paper put out on May 26, 2022, but it's the first time that I came across it. And as soon as I came across it, I knew that it was something that I should focus on my channel. So very straightforward, looking at the what this does very simplistically within the research paper is they take a normal transform model and they replace the tokenizer with a Fourier transform. So utilizing Fourier waves, and the model just reads and generates Fourier waves rather than normal tokens, and then it's able to create embeddings based off of that. And in this instance, they're able to create a full-on neural network based off of Fourier wave transforms, which is super interesting to me, right? And then so I wanted to recreate this on some level. And then so I have this here. And this notebook demonstrates an end-to-end implementation of a novel neural network architecture that combines learnable wavelet transforms with graph convolutional neural networks, so GCNs. So this is using wave transform and graph convolutional neural networks, which is why I know that there'll be a lot of people interested in this. And this model, referred to as integrates several key components. The first of all is a learnable wavelet layer, so a custom layer that performs continuous wavelet transforms on token embeddings with learnable scales. This layer extracts multiple scale features from the input sequence and later performs an inverse transform after convolutional modulation. A 1D convolution is applied to the wavelet transformed embeddings to modulate and refine the features before feeding them into the graph-based module. So essentially we take the data and then we shrink it into a 1D convolutional layer. Then we apply the graph convolutional network itself, which utilizes dependency graphs representing relationships between tokens to further process the embeddings. Multiple GCN layers capture local and global structural information from the graph. Then we apply a feed-forward network and an output layer. So this is completely feed-forward, no backpropagation. A 2-layer feed-forward, and in this instance, I up it to 3. A 3-layer feed-forward network processes the graph-enhanced features, leading to a final output layer that predicts classification targets and a custom dataset and a training pipeline. This notebook includes a custom text dataset class, dummy text generation, and a training loop that illustrates how to train the model. So I'm just using test and dummy data for this instance. I do have to load 2 packages, which are torch geometric, as well as pi wavelets. Pi wavelets will come up as PYWT, and then so if you try to pip install PYWT, you'll run into errors. It's pi wavelets. It's the full name, is the package name. And then going through here, so you can see here, I define the neural network, right? And then so the first thing that I need to do is define the wave function. So I do that, and then I define the wave function within the feed forward network itself. And then I have the inverse transform of the wave function. So a lot of math here. This whole thing is just for the inverse transform. And then we have the full module where everything comes together. So we have the layers, the convolutional module, the feed-forward network, etc. So this is essentially combining everything. This is our modified transformer layer here, right? So this 1 through 8, these are 1 through 8 are the different layers in our modified transformer network in this particular instance. And then we create our dummy data. And then so you can adjust the dimensions and anything you would like with the dummy data itself. And then I create the in this instance I do have in this first one the number of layers is set to 2, and then the model itself, and then we get essentially the first pass here I do is the shape of the model, and then this is my update version of the model here, and then this is where I update the model to more robust, and in general, this second code block here is my kind of production ready version of this model, right? And then so essentially it's all mostly the same. I'm just giving you more a lot more comments on the coding, especially what's going on around here, and then things that you can adjust within the code is kind of the main differences. And then when we go here down to the neural network itself, you can see that I've beefed up this network itself a bit, right? So hidden dimension 64 as opposed to 32, number of layers 3 as opposed to 2. And then I'm training it, I put a trainer on this instance, and I'm training it for 50 epochs and with a learning rate of 0.001. And I could adjust this down. I think if I put another 0 in here and this again, I might get better results than even what we're showing here. But Here, I set up the network, I set up the training loop, it's the forward pass, and then back propagation for the trainer. And then we go through, and we start off at 6.91 on the loss. So if you're not familiar, like this translates directly to coin flip accuracy, like 9% or so. So the model is like flat out guessing at this point, right? But what we can see is that the model is learning, right? This loss rate does go down. It goes down slowly, but then somewhere around like 35, 36 epochs around here, like it starts to like get better and converge better, right? So it's like a bunch of sixes and then high fives, and then all of a sudden it's like, okay, I'm going to start learning something here, right? And then by the end, it goes down to 3.7. So like, while it seems like very stuck up here, especially for like 10 epochs, if you ran for like 10 epochs, and that's what I did initially, 10 epochs. I was like, oh, this isn't doing anything. And then I sent it out to 50, and it's like, okay, this is needs some time to cook. And you give it some time to cook, and it'll actually find some information in there. And then so this is totally interesting to me. This 100% replaces tokenization, right? So the benefit of this model is there's no tokenizer in here, as you can see with any of the code that I've laid out here. And then you don't actually have a true like encoder and decoder, right? You're just encoding and decoding wavelets. And the wave transform. So it's super interesting. Like your wave transform is your decoder, which is super fascinating to me, how this is working overall. But so this architecture gets you a graph convolutional neural network at the end, which is what a lot of people want. And then it gives you access to Fourier transform for the transformers. And then so if you like this type of content, please like, subscribe. Thank you very much.